This is A. Radhika. I am going to give a video lecture on electrical engineering and electronics devices. The subject code is 18E to 05C. So today we are going to discuss about main topic is electrostats. But in this we are going to discuss dielectric strength and the importance of dielectric constant, capacitance and capacitance equation. So, before to going to this one, last class we discussed about electric potential and potential difference. So, actually, what is electric potential and potential difference? The electric potential at a point in an electric field is defined as the work done in bringing a unit positive charge, means 1 coulomb, from infinity to that point. It denoted by the letter V and is measured in volts. Electric potential V is work done by charge, that is equal to W by Q volts. An electric charge causes an electric field around it, which theoretically extends up to infinity. If any charge is placed in this dielectric field, it will be attracted or repelled depending on the nature of the charge. When it is moved, the work will be done against or by the force acting on the charge due to electric field. An electric charge causes an electric field around it, which theoretically extends up to infinity. If any charge is placed in this electric field, it will be attracted or repelled depending on the nature of the charge. When it is moved, the work will be done against or by the force acting on the charge due to electric field. Consider an isolated charge plus q coulomb is placed in the space. If a unit positive charge plus 1 coulomb is placed at infinity, the force on it is 0, because F is equal to 9 into 10 to the power of 9 Q into 1 by d square, as d to infinity, F to 0. If the unit positive charge is moved towards plus Q, a force of repulsion acts on it, because like charges repel each other. Hence, work is required to be done to bring it to a point like A. When the unit positive charge is at A, it has some amount of electrical potential energy, which we commonly call electric potential. The closer the point to the charge, the higher will be the electric potential at that point. Therefore, electrical potential at the point due to a charge depends upon the position of the point. The potential is 0 if the point is situated at infinity, and is maximum if it is situated near to it. It is clear that if the field is due to a positive charge, there is force of repulsion between plus q and unit positive charge, and hence work will be done against the electric field. However, if the field is due to negative charge, means minus q, there is a force of attraction between minus q and unity positive charge, and hence work will be done by the electric field. In practice, the potential energy or potential of the mass depends upon the position of the mass with respect to Earth. Hence, Earth is chosen as zero potential. It is because Earth is such a huge conductor that its potential practically remains constant. Hence, a body whose potential is higher than that of the Earth is said to have a positive potential, and one whose potential is lower than that of the Earth is said to have a negative potential. Hence, if a positively charged body is connected to Earth, charge will flow from the body of the Earth because the body has higher potential than the Earth. The charge continue to flow from positively charged body to Earth until the potential of the Earth also become the same as that of the body. Suppose if a negatively charged body is connected to Earth, charge will flow from the Earth to the body because the Earth has higher potential than the body. The charge continues to flow from Earth to negatively charged body until the potential of the body also becomes the same as that of the Earth. So here this is the potential and potential difference. So here today we are going to discuss about dielectric strength or breakdown voltage, potential gradient, and the importance of dielectric constant. Now, what is dielectric material? So here materials which have no free electrons and no conduction of electricity are known as insulating materials or dielectric materials. Means which materials have no free electrons and also it has no conduction. So that is that materials is called insulating materials or dielectric materials. Next, dielectric strength. The insulating property of dielectric is decided by a factor known as dielectric strength or break-even voltage. The property of dielectric depends on the nature of the material. Main definition is dielectric strength is defined as the property of a material or medium which enables it to withstand electric stress without damage or breakdown. The maximum voltage or maximum dielectric strength that the material or dielectric can withstand without rupture or breakdown is called dielectric strength. It is measured in kilovolts per mm or kilovolts per centimeter or kilowatts per meter. The maximum voltage or maximum dielectric stress that the material or dielectric can withstand without rupture or breakdown is called dielectric strength. It is measured in kilovolts per mm or kilovolts per centimeter or kilovolts per meter. The dielectric materials have few free electrons. When the applied voltage across such a material is gradually increased, some electrons may be detached from the dielectric, resulting in a small current to flow. If the applied voltage exceeds a critical value, then it allows a heavy electric current, means more than leakage current, to flow through it. Hence, the insulating properties of the dielectric are destroyed or ruptured and it becomes a conductor. Usually, a spark or arc occurs which burns up the material. The minimum voltage required to break down a dielectric is called breakdown voltage or dielectric strength. The dielectric strength is given as volt per T, kV per mm or kV per meter, where V is the breakdown potential and T is the thickness of the insulation and insulating or dielectric material. For example, the dielectric strength of air is 30 kV per centimeter. It means that the maximum potential difference which 1 centimeter thick which 1 centimeter thickness of air can withstand across it without breaking down is 30 kilovolts. If the potential difference exceeds this value, then air insulation breaks down, allowing large dielectric current to pass through it. The value of dielectric strength of a dielectric material decreases with the increase in thickness. The dielectric strength is usually affected by moisture, contamination, temperature, aging, mechanical stress, and shape. The dielectric materials have few free electrons. When the applied voltage across the dielectric materials have few free electrons when the applied voltage across such a material is gradually increased. Some electrons may be detached from the dielectric, resulting in a small current to flow. If the applied voltage exceeds a critical value, then it allows a heavy electric current, that is more than leakage current, to flow through it. Hence, the insulating properties of the dielectric are destroyed or ruptured and it becomes a conductor. Usually, a spark or arc occurs which burns up the material. The minimum voltage required to break down a dielectric is called breakdown voltage or dielectric strength. For example, the dielectric strength of air is 30 kV per centimeter. It means that that the maximum potential difference which 1 centimeter thickness of air can withstand across it without breaking without breaking down in 30 kV. If the potential difference exceeds this value, then air insulation breaks down, allowing large dielectric current to pass through it. The value of dielectric strength of a dielectric material decreases with the increase in thickness. The dielectric strength is usually affected by moisture, contamination, temperature, aging, mechanical strength, and shape. So, the dielectric material oppose the flow of current and provide insulation. They also provide a medium for storage of electric energy. So, this is the definition 1 for dielectric strength. The maximum voltage at which the dielectric can withstand without rupture is called dielectric strength. Unit C is kV per mm. Another definition for dielectric strength: the voltage required to puncture a dielectric or insulating material is known as breakdown voltage. The voltage required to puncture a dielectric or insulating material is known as breakdown voltage. At breakdown voltage, the dielectric material changes into a conductor. The breakdown voltage is proportional to thickness of the dielectric along the direction of field. The breakdown voltage is proportional to thickness of the dielectric along the direction of field. So, potential gradient. The potential gradient at any point in the electric field is defined as the rate of change of potential with the distance measured in the direction of electric force at that point. The potential gradient at any point in an electric field is defined as the rate of change of potential with the distance measured in the direction of electric force at that point. The potential gradient symbol is small g, and the equation G is equal to dV by dx, that E is equal to G, and the unit is volt per meter. Next, we go for importance of dielectric constant. Dielectric materials are essentially insulating materials in which the electrons are rigidly bound to their nucleus. Hence, ordinary field will not detach the free electron from nucleus, and hence no conduction of current through it. However, the dielectric material placed in an electrostatic field will be subjected to electrostatic conduction. Thus, a dielectric material will provide a medium for the storage of the electrical energy. The permittivity of a medium establishes electric flux lines within the dielectric. The permittivity of a dielectric material is a measure of the ease with which dielectric flux lines can be established within the dielectric. The dielectric materials are essentially insulating materials in which the electrons are rigidly bound to their nucleus. Hence, ordinary field will not detach the free electrons from nucleus, and hence no conduction of current through it. However, a dielectric material placed in an electrostatic field will be subjected to electrostatic conduction. Thus, a dielectric material will provide a medium for the storage of the electrical energy. The permittivity of a medium establishes electric flux lines within the dielectric. The permittivity of a dielectric material is a measure of the ease with which electric flux line can be established within the dielectric. The definition for dielectric constant is the ability of a dielectric material to concentrate electric lines of force in a medium is called dielectric constant or relative permittivity of that material. It is denoted by epsilon r. The ability of a dielectric material to concentrate electric lines of force in a medium is called dielectric constant or relative permittivity of that material. It is denoted by symbol epsilon r. The dielectric constant of A is 1 and is assigned a reference value of dielectric constant. The dielectric constant of all other insulating materials is greater than unity. The dielectric constants of different materials are given. The dielectric material stores energy. They are used in capacitors. The electric flux passing through the dielectric media depends on permittivity of the media. Hence, permittivity is the measure of the dielectric constant. The dielectric constant may be defined as the ratio of capacitance with the dielectric as medium to the capacitance of the same with air as dielectric. The dielectric constant may be defined as the ratio of capacitance with dielectric as a medium to the capacitance of the same with air as dielectric. So here we have the dielectric constant of some uh, dielectrics. So here vacuum the dielectric constant is 1. For air 1.006, for glass 4 to 6, mica 4 to 4.75 and paper 1.8 to 2.8 and ceramic 6 to 20, fiber 2 to 5, quartz 4.2 to 4.7 and rubber 2 to 3 and transformer oil the 4. So these values are the dielectric constants of dielectric materials. Next we go for capacitor. So here capacitor and capacitance. It is well known that different bodies hold different charge when potential is applied across it. This charge holding properly of a body is called capacitance or capacity of the body. The different bodies hold different charge when potential is applied across it. This charge holding property of a body is called capacitance or capacity of the body. The device which stores sufficient charge is known as capacitor or condenser. Any two conducting materials separated by an insulating material is known as capacitor or condenser. Any two conducting materials separated by any insulating material is known as capacitance or condenser. A capacitor is a device which stores the electrical energy in the form of electrostatic charge. A capacitor is a device which stores the electrical energy in the form of electrostatic charge. So, a capacitor consists of two conducting metal plates separated by an insulating medium, that is dielectric. You can observe in this diagram. Two are the conductive plates. The thickness distance is d, and that between two conductive plates it has the dielectric. A is the area of the conductive plate. So these are the capacitors. So capacitance definition 1. Capacitance of a capacitor is defined as the property to store electricity. The capacitance of a capacitor may be defined as the amount of charge required to create a unit potential difference across the plates. Symbol is C. Units is farad. 1 farad is equal to 1 coulomb per 1 volt. The capacitance of a capacitor may be defined as the amount of charge required to create a unit potential difference across the plates. So here the conducting materials are called plates of the capacitor and the insulating material is called dielectric. So here the conducting materials are called plates of the capacitor and the insulating material is called the dielectric. The conducting plates may be in the form of either circular or rectangular shape. The dielectric is a medium between the plates. The most commonly used dielectrics are air, mica, paper, ceramic, and electrolytic, etc. The commercial capacitors are generally classified according to the medium between the plates, such as air capacitors, paper capacitors, mica capacitors, ceramic capacitors, electrolytic capacitors, etc. A typical capacitor having two conducting plates A and B, which are separated by the means of air, a battery of V volts is connected across the capacitor plates. There are there are various types of capacitors such as parallel plate capacitors, spherical, cylindrical, but all types of capacitors consist of two conducting plates separated by an insulator or dielectric. The capacitors of parallel plate capacitor in which the plates are in parallel with each other. The symbol of capacitor is the parallel plate. Two, two conduction plates are taken. So next, how does capacitance stores in a capacitor? So that is the charging of the capacitor. So in this, let a battery of let a battery be connected across two plates of capacitor through a sensitive galvanometer. The galvanometer as switch is open. There is no current flow in the circuit figure. So in this figure it is the switch is open. So there is no deflection in galvanometer. So this is the parallel plate capacitor across a battery through a galvanometer and the key is open. P and Q are the capacitor conductors and C is the dielectric medium and B is the battery. So charging of capacitor. So here, so in this, a capacitor having plates A and B connected across a battery of V volts. The plate A is connected to positive terminal of the supply and plate B is connected to negative terminal of the supply. When the switch S is closed, the electrons from plate A will be attracted by the positive terminal of the battery and the electron starts accumulating on plate B. Now, plate A of the capacitor is deficient in electrons and thus it is positively charged. The plate B of the capacitor has an excess of electrons and gets negative charge equal in amount to the positive charge on plate A. The capacitor is said to be in a charged state. This process of charging continues till potential difference across the capacitor plates become equal to the battery voltage. When the capacitor is charged to battery voltage V, the current stops to flow. If now the switch is open, the capacitor will retain the charge. So this shows that the capacitor stores a charge. So here, suppose if the charge on each plate A and B is Q coulombs, the charge Q on each plate is directly proportional to the potential difference between the two plates, that is Q directly proportional to V. Since capacitors have the ability to store charge, they are also a source of electrical energy. This energy may be released slowly in some electrical circuits. Care must be taken uh, when touching capacitor because you can't tell if they are charged simply by looking at them, although they may be disconnected from the supply. They may still retain the charge and stores energy, can give a serious electrical shock. So, in this diagram, it is the parallel plate capacitor across a battery through a galvanometer and key. When key is closed, a field is established across the plates of the capacitor. Here, when switch is closed, positive terminal of the battery attracts some of the negatively charged electrons from plate P and move towards the plate Q. Hence, P gets positive charge and Q gets negatively charged. So here, hence, potential difference is developed between the plates. This transient flow of electrons causes a charging current and develop electric field across the plates. This electric fields increases as the electrons continue to move from plate P and Q. The flow of electrons ceases when the potential difference between the plates become equal and opposite to the battery EMF. So, discharging of capacitor. Now, the battery is removed and switch is open. then the field developed across the capacitor remains same as there is no way to move electrons. Now a resistor is connected across the capacitor and switch is closed. Electrical energy stored in the capacitor is dissipated in resistor. So these are the diagrams of discharging of a capacitor. When battery is removed and when the resistor is shunted across the switch. Next we go for parallel plate capacitor with uniform dielectric. So here parallel plate capacitor. So in this capacitance, the ability of a capacitor to store charge is known as its capacitance. Capacitance is the property of a capacitor to store electricity. The charge Q on each plate of a capacitor is directly proportional to the potential difference V between the two plates. So that is Q directly proportional to V. Q is equal to CV. C is equal to Q by V. C means capacitance and Q is equal to charge and V is equal to potential difference. C is the constant and is known as capacitance of the capacitor. Hence, capacitance of the capacitor can also be defined as the ratio of charge on capacitor to the potential difference between the plates, means C is equal to Q by V. The unit of capacitance is farad. The farad is very large unit, hence in practice it is convenient to use microfarad or nanofarad or picofarad. 1 microfarad is equal to 10 to the power of minus 6 farad. 1 nanofarad is equal to 10 to the power of minus 9 farad, and 1 picofarad is equal to 10 to the power of minus 12 farad. Capacitance of a capacitor. So in this parallel plate capacitor with the uniform dielectric, consider a parallel plate capacitor having two conducting plates A and B, each of area A meter square and separated by a uniform dielectric of thickness d meters and relative permittivity of epsilon r. If a potential difference of V volts is applied across the plates, then a charge of plus Q and minus Q coulombs induced on plates A and B respectively. Let E and D be the dielectric intensity and flux density between the plates. In this, Q charge on each plate in coulombs. A is the cross section area of the each plate, that is in meter square. D is the electric flux density, coulomb per meter square, and E is equal to electric intensity, V per meter. So in this diagram we can observe that it has the two plates and it has the positive charge, and one plate has the negative charge. Between the two plates it has the dielectric material. The distance between two plates are small d. In this, V is equal to potential difference across the plates. Epsilon r is equal to relative permittivity. D is equal to Q by A C by meter square, coulomb per meter square. E is equal to D by epsilon, that is equal to Q by epsilon naught epsilon r V by M. So here V is equal to E into D, that is equal to Q by epsilon naught epsilon r A into D. From this, Q by V is equal to epsilon naught epsilon r A by D. So here C is equal to epsilon naught epsilon r A by D, coulomb per volt or farad. So here parallel plate capacitor with compound dielectric. In this, the capacitor in uniform dielectric, the capacitance C is equal to epsilon naught epsilon r A by D. The capacitance of a capacitor is directly proportional to the area of the plates, directly proportional to the relative permittivity of the medium between the plates, inversely proportional to the distance between the plates. Next, we go for parallel plate capacitor with composite medium. Parallel plate capacitor with a compound dielectric. In this, we can consider two dielectric mediums between positive plate and negative plate. The distance is d1 and d2. So here the parallel plate capacitor with the compound dielectric, suppose the space between the plates A and B is occupied by two dielectrics of thickness d1 and d2 with relative permittivities epsilon r1 and epsilon r2 respectively. The dielectric flux density d remains the same in all dielectrics. V is the potential difference across the plate and V1, V2 be the potential difference across the two dielectrics. So here, so in this, E1 is equal to d by epsilon naught epsilon r1 and E2 is equal to d by epsilon naught epsilon r2. Total V is equal to V1 plus V2, that is equal to E1 into D1 plus E2 into D2, that is equal to Q by epsilon naught epsilon R1 into D1 plus Q by epsilon naught epsilon R2 into D2. So that is equal to Q by epsilon naught A takes common and remaining is d1 by epsilon r1 plus d2 by epsilon r2 volts. So here parallel plate capacitor with the compound dielectric. Q by V is equal to epsilon naught A by d1 by epsilon r1 plus d2 by epsilon r2 farad, and also Q by V is equal to epsilon naught A by d1 by epsilon r1 plus d2 by epsilon r2 farad. So here Q by V is equal to C, that is equal to epsilon naught A by d1 by epsilon r1 plus d2 by epsilon r2 farad. In general, C is equal to epsilon naught A by d1 by epsilon r1 plus d2 by epsilon r2 plus so on, or C is equal to epsilon naught A by sigma d by epsilon r. So in this, capacitance of a variable capacitor. So in this capacitance, it has the many number of dielectric materials. If n plates are arranged, then the equivalent capacitance C is equal to n minus 1 epsilon naught epsilon r a by d farad. In case of we can consider n number of plates with different dielectric materials. So here now we go for solving the few problems related to dielectric constant. So here a capacitor is made of two plates with an area of 11 centimeter square and separated by mica sheet of 2 mm thick. If for mica the relative permittivity is 6, find its capacitance if one of the plate is moved further to give an air gap of 0.5 mm between the plates and mica. Find the find the change in capacitance. So here a capacitor is made of two plates with an area of 11 centimeter square. The given area and separated by mica sheet of 2 mm thick. 2 mm thick. If for mica the relative permittivity is 6, find its capacitance. If one of the plate is moved further to give an air gap of 0.5 mm between the plates and mica, find the charge in capacitance. So here the given data is area is equal to 11 into 10 to the power of minus 4 meter square. Here they given in centimeter square, we can convert in meter square. Area is equal to 11 into 10 to the power minus 4 meter square, and d1 is equal to 2 into 10 to the 2 into 10 to the power of minus 3 meter. Epsilon r1 is equal to 6. If d2 is equal to 0.5 into 10 to the power of minus 3 meters, find out the C1 and delta C. So here the formula is equal to C1 is equal to epsilon naught epsilon R1 A by D1. This is the formula for say capacitance. So we can substitute in this the values. So epsilon naught is equal to 8.854 into 10 to the power of minus 12 into 6 into 11 into 10 to the power of minus 4 by 2 into 10 to the power minus 3. So after calculation of this one, we will get 29.22 into 10 to the power of minus 12 farad, that is equal to 29.22 picofarad. This is the answer for capacitance. Next, for new capacitance, C2 is equal to epsilon naught A D1 by epsilon R1 plus D2 by epsilon R2, that is equal to 8.854 into 10 to the power of minus 12 into 11 into 10 to the power of minus 4 by 2 into 10 to the power of minus 3 by 6 plus 0.5 into 10 to the power of minus 3. After calculation of this one, we will get 11.687 into 10 to the power minus 12 farad, or 11.687 picofarad. And also change in capacitance delta C is equal to C1 minus C2, that is equal to 29.22 minus 11.687. into 10 to the power of minus 12, that is equal to 17.533 picofarad. Next we go for another problem. A capacitor consists of 10 similar square aluminum plates, each 10 centimeter, each plate 10 centimeter by 10 centimeter, mounted parallel to each other. Alternate plates are electrically connected to give two terminals. What is the capacitance between the terminals when distance between any two plates is 1 centimeter and the dielectric is air? A capacitor consists of 10 similar square aluminum plates, each 10 centimeter by 10 centimeter, mounted parallel to each other. Alternate plates are electrically connected to give two terminals. What is the capacitance between the terminals when distance between any two plates is 1 centimeter and the dielectric is air? The solution is the given n is equal to 10, a is equal to 10 into 10 to the power minus 4 in meter square, d is equal to 1 into 10 to the power of minus 2 meters, epsilon r is equal to 1 because it is a. Find out the capacitance C. We know that C is equal to n minus 1 into epsilon naught epsilon r a by d. So we can substitute in this. The values are 10 minus 1, 8.854 into 10 to the power of minus 12 into 1 into 100 into 10 to the power of minus 4 by 1 into 10 to the power of minus 12. So that is equal to, sir, minus 2, that is equal to 7.9686 into 10 to the power minus 11 farads, or 79.686 picofarads. So this is the answer for questions. We have few quiz questions. The capacitance of a parallel plate capacitor with uniform dielectric is C is equal to sigma permittivity, absolute permittivity and relative permittivity A by D. The capacitance of a parallel plate capacitor with the compound dielectric is C is equal to epsilon naught A by D1 by epsilon R1 R1 plus D by epsilon R2 plus so on. The unit of capacitance is farad. The equation of capacitance C is equal to Q by V. Here these are the few ask few frequently asked questions. Define capacitance and explain the charging of capacitance with the neat diagram. So this is the today's class of capacitance. Thank you.